Okay, thank you for the introduction. I'm Oren Salzman. I'm a postdoc here at Carnegie Mellon University. I'm going to talk about efficient motion planning for problems lacking optimal substructure. And this is joint work with Brian Hu and Srinivasa. So at the Personal Robotics Lab, some of the work we do is assisting people with high spinal cord injuries. And we have a planning paradigm which is called shared autonomy, where the user controls a robotic arm, which is attached to his wheelchair, but the planner also estimates the user's intention and assists him in the planning. And in this specific example, we have the user which needs to pour water from the pitcher. And we have two possible configurations. The first on the top is where the user can see the end effector of the robot, or the hand of the robot, and the pitcher, and that's great. And the second is when the robot occludes the end effector and the pitcher from the viewpoint of the user. And this is something which we want to avoid. This is a soft constraint in the sense that we don't want to avoid these situations and restrict the planner not to take them, but we want to penalize the planner taking these type of configurations in its motion. So we call these risk regions, where the end effector is occluded from the viewpoint of the user. Now, these risk regions are not confined to this specific examples. Think of a robot that needs to continuously localize itself, so it has landmarks. And we want it to plan a motion while being visible to these landmarks, and we want to penalize it when it's not visible to the landmarks. A somewhat complementary case is where we want to plan for occluded motion. So we have some threat, say a sniper at the top of the building, and we want to plan an occluded motion from point A to point B. And in all these examples, being exposed to the risk, say for 10 one-second intervals, is much better than being in the risk region for a long period, say 1 10-second intervals. So this is the notion of being penalized to exposure to risk in a super linear fashion. So in this problem, we want to balance between minimizing path length and minimizing exposure to risk in this weird super linear fashion. So here I have an example on the top, which I'm going to come back to at the end of the talk, which mimics old Viking expeditions from Norway to Newfoundland. And sailing the seas, the Viking could take the safe route, which means following the coastal line. So this is the red path that you can see on the top, which follows the coastal line as much as possible. They could have taken the shortest path, which is the green route that takes the shortest path from Norway to Newfoundland. Or, assuming they had a cost function that I'm going to talk about, they could have planned a path that balances between being short and being exposed to risk. So the contributions of this work are twofold. First, we're going to define a cost function that simultaneously balances path length and this exposure to risk, where we penalize exposure superlinearly. And then I'm going to present two algorithms that plan minimal cost paths under this cost function. So there's a lot of related work that is relevant to this work. Our domain is from the continuous motion planning domain, so there's a lot of work on continuous motion planning. Path planning on discrete graphs is super relevant here, especially not additive cost functions because of the structure of our cost functions, and multi-objective path planning, and obviously planning under risk constraint. So these are all relevant work. Now, to define the problem, I'm going to take this toy example where we have a threat in the middle. We have our configuration space, which is subdivided into the free space, here depicted in white and purple, and the obstacle space, here depicted in red. The free space is further subdivided into the risk region, the purple region here, and the safe region, which is the right region. And we have trajectories, which are mappings between time and the free space. And in this talk, I'm going to assume that the robot moves at constant speed. This is only for the sake of the talk. So we can talk about path length and duration interchangeably. So before I can talk about the cost function, I need to define the notion of current exposure time. So let's look at a trajectory at the top right here, which moves between the safe region into the risk region and then back into the safe region. So we say that the current exposure time is simply the time passed since the robot entered the risk region. So if we are in the safe region, this is simply 0. And if we're in the risk region, this grows linearly as the trajectory passes through the risk region. Once we enter the safe region again, then the current exposure time drops down to 0. Now, we want our cost function to grow linearly when we're in the safe region. When we enter the risk region, we want it to grow superlinearly, as we can see here. And then when we exit the risk region, we want it to continue to grow linearly. So the cost function that we present here, and this is one example, we have a generalization of this in the paper, is simply taking the exponent of the current exposure time of the trajectory taken. Now that we have this notion of a cost function, we can define the planning problem that we want to solve. So risk-aware motion problem in this context, we have a planning domain, namely the safe region, the risk region, and the obstacle region, as well as a start and a goal. And we want to plan a path connecting the start and the goal, minimizing the cost function that I just defined. However, this continuous problem is p-space hard. So in this talk, I'm going to concentrate on the discrete version of this problem. So we have the same problem, but we have a pre-computed graph, which we can think of as the PRM roadmap, which is a graph embedded in this continuous space. And now we want to plan a minimal cost path on this graph between a start and a goal node. Now the first question one should ask is, why not use standard pathfinding algorithms like Dijkstra? So these algorithms assume that the cost function has an optimal substructure, namely that subpaths of an optimal path are also optimal. So what is this visualization? This is a visualization of basically how Dijkstra works. We have a bunch of snails leaving the source node, and they all move at constant speed. And once a snail reaches a vertex, no other snail can reach that vertex, a future vertex before him. So we can just, once two snails meet, they can just retract into the shell and stop continuing. However, in our case, we have a cost function that does not have an optimal substructure. Namely, subpaths of optimal paths may not be optimal. So let's look at this cartoon depiction. Assume that when a snail enters the risk region, it starts to slow down. For the sake of the example, it accumulates muck on its foot and it slows down. Now, it'll restart in a second. The green snail reaches vertex y before the red snail. So that's the optimal path to reach vertex y is via the green snail. However, it spends longer in the risk region, so it's much slower than the red snail. So what happens here is that although the red snail reaches vertex y after the green snail, it can actually catch up with him and can reach the future vertex z before the green snail. And this is because of this non-optimal substructure that we have in this case. So standard pathfinding algorithms can't work, so we need to do some tweaking here. However, the cost function does have some structure. If this is the cost function, note that if we're in the safe region, and this means that the current exposure time is 0, then the cost for this part of the trajectory is simply the duration of the cost, or its length. If the trajectory is only in the risk region, then we have an analytic solution for the cost. And these two kind of natural and simple observations hold for any maximal connected subpaths that only stays in the safe or the risk region. So using these observations, we can present the first algorithmic approach, which is pretty straightforward. We do some pre-computation. We split our graph, our roadmap, into subpaths that only stay in the safe region and only stay in the risk region. And for this, we need to compute border points. Border points are the intersections of edges with the boundary of the safe region and the risk region. Then we compute the all pairs of paths, optimal paths between border point. And for this we can use Dijkstra, because within the risk region we do have an optimal structure of these paths. And then we can define a new graph which has an edge between every pair of points according to the pre-computed distance, and run your favorite path planning algorithm, Dijkstra, A*, whatever. So it's nice because this allows us for multiple queries and it's straightforward to implement. However, this is super sensitive to the number of boundary points. I'm going to talk about computational complexity in a few slides. And we need to pre-evaluate all edges in the roadmap. And the path planning problem that we considered is kind of a single query. So it takes a lot of time and we're going to see it. If we want some online algorithm, we need to use the notion of domination and useful paths. So we say that one trajectory dominates the other if it's always better to use it to reach some future vertex. So in the analogy of snails, if one snail is before another snail and it has less muck on its foot, so formally one trajectory dominates the other if its cost is equal or smaller to the other trajectory's cost, and the current exposure time is smaller or equal to the other trajectory's cost. And using the notion of domination, we can have the notion of a useful set of trajectories. So we say that a trajectory is useful if a set is useful if no two trajectories dominate each other. Now I'm not going to go into the details, but using the notion of domination and useful set, we can have a Dijkstra type algorithm which is incremental, and on the fly we maintain basically which snails are relevant at each point of time. So for vertex y here, we need to maintain both the green and the red snail, because the green snail reached it before the red snail. However, the red snail has less muck on its foot, or its exposure time is smaller. For vertex z here, we can prune away the green snail because the red snail both passed him and has less exposure to risk. So let's talk about computational complexity. If n is the number of vertices, m is the number of edges, and nb is the number of border vertices, then plain old Dijkstra, which is just given here for a reference, takes time n log n plus m. The pre-processing based algorithm has a factor of nb squared and nb times n, which is what caused it to be that slow. While our incremental based algorithm in the worst case runs in time nbm plus nbn log n. Let's look at some experiments. So first we have the toy example that I talked about earlier, where we have we're trying to follow the Viking expeditions, and the obstacles here are the land masses. The coastal regions, which we can see here in white, are the safe region, and all the open sea is risk. And just for the sake of visualization, we have here different paths computed, either minimizing risk, risk aware, or just plain old shortest path. The second scenario that we're going to consider is the original assistive care setting, where here we have obstacles. The obstacle region is any configuration where the robot intersects itself, the user, the table. The safe region are all the configurations that are visible where the bottle is visible to the robot. And the risk regions are the complementary. And we ran the three algorithms. So we ran Dijkstra, which only computes minimal length paths, but this is just as a reference. And for the risk-aware paths, we computed both the pre-computation-based algorithm that I presented, as well as the incremental-based one. For the toy scenarios, Iceland and Norway, we see that Dijkstra's algorithm computes it within several tens of milliseconds. And our incremental-based algorithm is roughly an order of magnitude longer, but it computes a much more general cost function. The pre-computation-based algorithm is just hundreds of seconds because it needs to pre-process this entire graph. And for the assistive care scenario, it terminated early due to lack of memory. So everything just exploded there. Interestingly, Dijkstra's algorithm actually took several orders of magnitude longer than our incremental-based algorithm. And this is because in that specific scenario, most of the region was risk region, and Dijkstra's algorithm didn't take that into account, while our algorithm kind of naturally was biased to go through the safe region. So this is really what we wanted to happen, which was nice. Future work. So we started this work with a continuous domain. We had to shift it to the discrete domain in order to find algorithms that were tractable. So now we want to come back to the to the continuous domain. We want to see if we can apply standard sampling-based algorithms to this domain, so PRM star and RT star. There's an interesting theoretic aspect if these algorithms are still optimal under this specific cost function. We're very interested in the low-dimensional setting where we have a planar case. Can we give either exact or even approximate algorithms for this specific planar case? And we're really excited about applying this notion of safe region to the notion of compliant or fine motion planning. So basically here the safe region is a low-dimensional manifold in the continuous C-space. That concludes my talk. Thank you.
Any questions? Gideon?
Yeah. So can you comment a little bit more on PRM star and RT star as to why they would not be subjectively optimal in this setting? And the other question, since I have it here, can you incorporate costs that are non-uniform? Because there are sampling-based motion planners that work with any kind of cost map where the cost can vary from any region to any other region, while here it seems that you only have one type of cost.
So the first question, the assumption, if you look at the proof on the optimality of PRM star and RT star, basically you have a continuous region around the optimal path where you slightly approach this path. And what we have here is we have these switching domains between the safe region and the risk region where you don't have this convergence. So you don't have this nice ball around each point where if you're close, if you're on this ball, then you can say that you gradually approach the optimal path. And can you remind me of the second question?
There are like TRRT, for example, transition-based that operate on any kind of cost map where you have a cost defined at any point on the environment or on the configuration space, so they would seem difficult to this kind of.
Yeah, that's a good question. The problem is that history matters in our case. So it's not only the state where you're at, so the cost map is not mapping between configurations and cost, but every state has a history. How much time have we spent in the risk region? So you need to take this additional dimension into account. That's the short answer.
Okay. I think we need to take the other question offline. So let's take again the speaker. Let's know when you have 5 minutes.